Okay, here goes. What are we doing? Practice free response. So, simple harmonic motion, we're dealing with a mass on a spring, and let's see, scoot over there, solutions. So, what we're dealing with is, well, complicated. So, this is a released AP question from a couple years ago. We have 20 kilogram box on a horizontal friction. The surface is moving to the right at a speed of 4 meters per second. The box hits and remains attached to one end of a spring, negligible mass, of course, whose other end is attached to a wall. So let's see our diagram, right? So as I'm reading, I would be drawing for sure. Here's our box, here's our speed, here's our spring attached to the wall, and it tells us that once it hits, it remains attached and it oscillates back and forth, where the maximum compression of the spring is half a meter. So that's our question. Part A says the spring does work on the box from the moment the box first hits the spring to the moment the spring reaches maximum compression. Indicate whether the work done by the spring is positive, negative, zero. So when I read this, didn't read carefully enough, so we're about to see my solutions and they're wrong. So indicate whether the work done by the spring, so here's the box, and we're talking about the spring. As the box compresses the spring is obviously pushing in this direction. So let's see what I wrote. I said, ooh, this is going to get messy. I said positive work on the spring, forces in the same direction as motion. The box does positive work on the spring, but the spring does negative work on the box. And the reason is because the force and the direction of motion are opposite. So when we're talking about the spring doing work on the box, it is negative. This is similar to you holding something and lowering it down to the ground at a constant speed. You're pushing upward, yet the thing is moving downward, so you're actually doing negative work. Alright, so okay, that'll be alright. Let's see, part 2, calculate the magnitude of the work described in part 1. So the reality is that the box has some kinetic energy. Yes, this is going to get messy. The box has some kinetic energy as it's moving, 1/2 mv squared, and that turns into elastic potential energy stored in the spring. So this is the amount of work done. The box pushes on the spring and exerts some force. And if you're thinking, well, why don't we just do force times distance? That's good. You at least know what we're talking about when we're talking about work, right? So force, the mass exerts some force on the spring through some distance as it compresses. But the force actually changes as the spring gets compressed, so that would be more of a calculus question. But kinetic energy of the box before it hits the spring is all turned into elastic potential energy. That's the work done by the box, so 160 joules. Part B, so that was calculate the magnitude of work, 160 joules. Magnitude just means amount. Part B, calculate the spring constant of the spring. So we know F equals negative kx, and we can kind of just think of that as F equals kx. Let's see, where are we? Right here. Okay. So, right, we know F equals kx, or negative kx, for force, spring constant, and displacement. And we also know that the potential energy is a 1/2 kx squared. So I think that's what I used here. In order to calculate the spring constant, if we know that the maximum potential energy at a compression of 1/2 meter is 160 joules, we can plug in 160 joules, 1/2 k, and then the maximum compression, or the compression at which the spring has 160 joules of potential energy. So we get k of 1,280 newtons per meter, which is springier than the springs that we have used in class, but not excessively. All right, spring constant of the spring. Next, we're going to calculate the magnitude of the maximum acceleration of the box. Maximum acceleration of the box. And so you're wondering where that would be, right? The mass hits the spring, and then it's going to spring and spring and spring and spring and spring and spring and spring. Remember, at the equilibrium position, that's where acceleration is 0. And out at the ends, maximum and maximum acceleration. So as it's compressed fully, so here's what I say. When it's compressed fully, we can actually calculate the force, and that will give us force equals mass times acceleration. So F equals ma will give us acceleration. Force provided by the spring is given by F equals negative kx. So we're going to plug in here first to find force, and then we can solve for acceleration. So here's our spring constant. Here's our maximum displacement from equilibrium, or maximum compression of the spring. And we get this number, 640 newtons, and there's a negative sign there, which just means that as the spring, where's our spring? Take over. Here's the wall. All right, so here's equilibrium position, and here's maximum compression where the spring's really squished up. Right, and this was 0.5 meter, so when it's maximally compressed, that's when the spring is giving the maximum force, and so the acceleration of the box is at a maximum. And notice how it is to the left. So F equals ma gives us an acceleration of 32 meters per second squared to the left. And then as the box is out here, the acceleration will be to the right. Whew. So the magnitude of maximum acceleration. So I didn't really even have to put that negative in there. It's just 32 meters per second squared. D, calculate the frequency of oscillation of the box. So frequency of oscillation, that's on the other page. Sorry about that. We'll go write it by hand, no problemo. Although this one's going to be a problem, but whatever. Okay, frequency of oscillation of the box. So we know that the period of oscillation and frequency, those are reciprocals, and we can calculate the period of oscillation once we know the mass and the spring constant. So we have 2 pi square root of m, and that was 20 kilograms over k. Let's make sure it wasn't 40. 20 kilograms, sounds good. Alright, so we're going to plug that into the calculator and get some number, and then we're going to do 1 over that number to get the frequency, which I solved on the next page, unfortunately. So what we get is 1.27, and so that would be oscillations per second, which is also known as hertz, Hz, hertz. Alright, so what are we saying? Our answer is 1.27 hertz, or oscillations per second, frequency of oscillation of the box. Alright, E, let's see, you little pesky, get out of there. Alright, so question E, let x equals 0 be the point where the box makes contact with the spring with the positive x direction toward the right. Okay, positive, negative. On the axes below, sketch the kinetic energy K of the oscillating box as a function of the position for the range, so between here and here. So this is where the box hits the spring, and then it's oscillating back and forth like this, and we're supposed to graph the kinetic energy. What would it look like? So kinetic energy is always going to be positive. Stuff's going to be up here. And we know that, did we calculate our maximum kinetic energy? I thought we did. Maybe it's here on these guys. Oh yeah, 160 joules. Cool. So we could actually put a number in there. 160 joules. And When the box is moving fastest in the middle, it has maximum kinetic energy, and then out at the ends, it's going to have 0, right? Because it's not moving here, and it's not moving here as it moves back and forth. And remember, so is it like this? Well, that's close, but it's actually not correct. Our formula for the potential energy of a spring, 1/2 kx squared. Notice how it depends on the square of the displacement. So if we were graphing potential energy, it would look like this parabola. So I'm going to put that in right here. Potential energy would be like this, in which case the kinetic energy is going to mimic that, but be in the opposite direction. So our kinetic energy would look something like this, some downward facing parabola, where it maxes out at 160 joules, and then goes to 0 and goes to 0. Okay, I think we can finish this one in the remaining 4 minutes that we have. Oh goody, you say. So our last, so yeah, there was all that stuff. Our last question, on the axis below, sketch the acceleration of the oscillating box as a function of position for the range. Okay, so here's acceleration. And here is maximal compression and then maximum stretch, right? So things moving back and forth. So let's think about what happens when the box is over here, okay? It's got a whole lot of force in this direction, meaning it has a negative acceleration, an acceleration in the negative direction. When the box is here at equilibrium position, right? The spring is actually exerting no force on it, and the acceleration is 0. Let's plot that point now that we know it. Acceleration is 0, and then we can anticipate when the box is over here, the spring is really pulling on it. So it has an acceleration in this direction, and that is the positive direction, that is the negative direction. So, and then lastly, if we look at this, F equals negative kx, we see that the force, thus the acceleration, I'm going to use some math speak here, watch out, varies linearly with the displacement from equilibrium, meaning, scare you with big words. So this is a line, equation of a line. It's like y equals mx plus b, where this would be the slope. So we could do that, right? We got some negative value, 0 value, positive value, and we're looking for acceleration, which we actually calculated. So if we were trying to be really cool, we would put a number up there. Acceleration is 32 meters per second squared, and down here, negative 32 meters per second squared. Whoo! That was good.